Hello everyone, my name is Mihat Saberi from University of Oxford. Today I will present our work on the loading rate effect on monopile foundations for offshore wind turbines. This work was carried out together with Professor Guy Halsby and Professor Byron Bear. During this presentation, I will give you first some introduction and then I will talk about the high sand constitutive model that we developed and implemented, and then model calibration and monopile finite element simulation, and then I will show you the numerical results and finally some conclusions. Monopile foundations are currently the most widely used foundation type for offshore wind turbines, especially in shallow waters. They typically consist of large diameter steel piles with length to diameter ratios between 3 and 8. Offshore wind turbines are subjected to combined loading by wind and waves, which lead to lateral loads and overturning moments acting on monopile and needs to be considered in the design process. Under this condition, the loading rate becomes very important, particularly in partially drained condition, where the soil response depends on how quickly the loads are applied. This can lead to development of positive or negative excess pore pressure, which in turn affects significantly pile capacity. In addition to laboratory and field testing, finite element modeling is a useful tool for understanding the behavior of monopile foundation and useful for the design and analysis of this structure in practice. So in this study, we therefore use three-dimensional finite element modeling to investigate the loading rate effect on the monopile foundations. For a proper finite element simulation, one of the important components is appropriate simulation of soil behavior. So for this purpose, we need an appropriate soil constitutive model capable of simulating the advanced behavior of the soil material. For this purpose, in this study, we developed a high sand constitutive model and we implemented into the finite element code. High sand is a hyperplasticity-based effective stress model consistent with thermodynamic principle. The advantage of this model is all constitutive equations can be derived using two scalar functions. One of them is Gibbs energy function and another one is the yield function. The equation related to triaxial condition is presented here. For example, for Gibbs energy function, the energy function consists of three main parts. The first part is related to nonlinear elasticity. The second part is related to plastic strain, and the last part is related to consolidation mechanism. After developing the model, the next step was model calibration, and we need to obtain the input parameters of the high sand model. High sand has 14 input parameters. They can easily be obtained using the data of triaxial test. So in this study, we use the Karlsruhe sand and corresponding triaxial test data under both drain and undrained condition. So you can see there is a very good agreement between molar prediction and triaxial test data. So the solid lines are the test data and the dotted lines are the high sand model. So for the figure on the top, you can see the comparison in deviatoric stress against shear strain for both drain and undrained condition. And for the drain test on the bottom left, you can see volumetric strain against shear strain. And as you can see, the model very well simulates the contractile behavior for the loose sands and also initial compaction followed by dilation for the dense sands. And for the undrained test, in the bottom right, you can see the stress path variation in deviatoric stress against effective mean stress space. After calibrating the model, we use the input parameter that we obtain from the calibration for simulating the whole problem using finite element model. As you can see here, this is the geometry that we created for this study. So the soil is simulated using solid element and the pile was simulated using the shell elements. So the pile was steel material with a medium scale size. Diameter is 1.22 meter and L over D ratio was 3. They applied the load laterally on the pile head with different rates, ranging from very low rate 0 to high rate of 100 millimeter per second, in order to simulate drained condition, partially drained, and close to undrained condition. As you can see, the model is symmetrical because of the geometry of the problem, and also we consider a wide range of density from loose to very dense, and we investigate the effect of loading rate on the pile capacity. The analysis was hydromechanical analysis in order to properly simulate the variation of excess pore pressure and effective stress at the same time. Now let's see some numerical results. I'm going to show you the variation of pile capacity against ground level displacement for two cases, loose sand and dense sand. Vertical axis is pile capacity normalized by the drained capacity after 10% of diameter displacement at ground level, and horizontal axis is ground level displacement normalized by diameter. First, for the loose sand, as you can see, by increasing the loading rate, the pile capacity drops significantly, which is because of the contractant behavior of the loose sand. During this contraction, so the excess pore pressure increased positively, which results in significant reduction in effective stress and pile capacity. But the story is different for dense sand. So because the dense sand shows dilation behavior, and you can see by increasing the loading rate, the pile capacity is significantly increased because after initial compaction, so the phase transformation happens and the soil goes to dilation behavior, which results in an increase of excess pore pressure in negative direction, which results in an increase of effective stress and consequently increase in capacity. Now let's combine the results into a one graph, which is a very useful graph for the design practice. So this is variation of pile capacity against loading rate for sands with different densities from loose to dense. So pile capacity is normalized with the drain capacity, and the loading rate is normalized with mean velocity of drain and undrained condition. As you can see in this graph, so when the loading rate is low, the behavior is almost drained. When the loading rate is increased, the behavior would be partially drained, and for high rate that the capacity change is almost stabilized is close to undrained. As you can see for the loose sample, during the partially drained condition, increasing the loading rate results in a reduction in pile capacity, but by increasing the density, the behavior is changed, and you can see for medium dense to very dense, by increasing the loading rate, the capacity is significantly increased under partially drained until reaching the undrained condition. Let's talk about some conclusions now. In this study, many three-dimensional finite element simulations were carried out on laterally loaded monopile under different loading rates from low to high to simulate drained, partially drained, and undrained condition using the high sand constitutive model. The numerical predictions show consistent and realistic trend across a wide range of loading rates. For the dense sand with dilatant behavior, excess pore pressure initially develops positively and then transition to negative values because of the phase transformation. It increases effective stress and enhancing monopile resistance compared with drain condition. The story is different for loose sand with contractant behavior because excess pore pressure remains positive during the loading, which reduces effective stress and results in reduction in monopile resistance relative to drain behavior. And overall, loading rate increases monopile capacity in dense sand and reduces capacity in loose sand.